Hey there! Welcome to today's lesson on energy conservation. Now, before we get into the equations, let me ask you something. Have you ever dropped the ball from a height and watched it speed up as it falls? What's happening there? Well, it's perfect physics. It's called the conservation of mechanical energy. But what exactly is mechanical energy? Mechanical energy is the total energy a system has due to its motion and position. It's a sum of two types of energy, kinetic energy, which is the energy of motion, and potential energy, the energy stored by an object's position. So, here's the big idea. When there are no energy eaters like friction or air resistance, the total mechanical energy, the combination of kinetic and potential energy, stays the same. It's like a perfect balance where potential energy turns into kinetic energy and vice versa without any loss. Let's take a closer look at this balance. Picture a ball hanging in the air. It's not moving, so its kinetic energy is zero, but it has potential energy because it's high up. Now, what happens when you let go of that ball? It starts falling, right? As it falls, its potential energy starts turning into kinetic energy, the ball speeds up. By the time it hits the ground, all that potential energy has been converted into kinetic energy. This is where the magic happens. The total mechanical energy, the sum of potential and kinetic, stays constant throughout the fall. The formula to remember is simple: delta K, change in kinetic energy, plus delta V, change in potential energy, equals 0. In other words, the total energy at the start is equal to the total energy at the end. It's like a perfect trade-off between speed and height, and the total energy never changes. Hello everyone. Let's dive into the fascinating connection between work and energy through the work-energy theorem. The theorem tells us something very powerful. The net work done by all the forces on an object is equal to the change in its kinetic energy. In symbols, that's written as W net equals delta K, which is K final minus K initial. Now, when we talk about conservative forces, like gravity or spring force, the work they do doesn't disappear. Instead, it transforms into potential energy. This ensures that the total mechanical energy of the system remains constant. That relationship can be beautifully summarized as delta K plus delta V equals 0. In simpler words, whenever a conservative force does work, it just shuffles energy back and forth between kinetic and potential forms, never losing the total amount. So, the work-energy theorem is really the bridge that connects forces to the energy transformations we observe in motion. Now, let's make this real. Imagine you're standing on top of a 10-meter high cliff, holding a ball. What happens when you drop the ball? It falls, right? As it falls, its potential energy turns into kinetic energy. We can actually calculate how fast it's going just before it hits the ground. Here's how. The potential energy at the top is mass times gravity times height, so 2 kilograms times 10 meters per second squared times 10 meters. That gives us the total potential energy. By applying the principle of energy conservation, we equate the two. mgh equals 1/2 mb squared. Simplifying, we find that V equals the square root of 2gh. This gives us a final velocity of V equals the square root of 2 times gravity times height, which is 14.14 meters per second. So, from height to speed, the total mechanical energy stays the same. It's just converting from one form to another. Let's switch gears for a moment and look at something a little bouncier, a spring. Picture a block attached to a spring. Now, when you stretch or compress the spring, you're storing potential energy in it. The more you stretch or compress, the more energy gets stored. When you let go of the block, the spring does work on it, turning that stored potential energy into kinetic energy as the block speeds up. Just like with the falling ball, the total mechanical energy remains constant, it's just transferring between kinetic and potential energy. We can sum this up with the equation energy equals kinetic energy plus potential energy equals constant. The total mechanical energy doesn't change, it's always the same, just swapping back and forth between motion and position. Alright, time for a real-world example to see how this works in action. Let's say we drop a 2 kg object from a height of 10 meters. We want to find out how fast it's going just before it hits the ground. We can use the energy conservation formula, mass times gravity times height equals 1/2 times mass times velocity squared. Now, plugging in the values, 2 times 10 times 10 equals 1/2 times 2 times v squared. After simplifying, we find that v equals the square root of 2 times gravity times height, which is 14.14 meters per second. So, as we expected, the speed at the bottom is 14.14 meters per second. This confirms that energy is conserved as the potential energy at the top is completely converted to kinetic energy by the time the object reaches the ground. Let's wrap this up. The conservation of mechanical energy is a super powerful principle. It tells us that when no non-conservative forces like friction are involved, the total mechanical energy of a system remains constant. Whether you're dealing with a ball falling, a pendulum swinging, or a spring bouncing, the energy just shifts between potential and kinetic forms without any loss. This principle is at the heart of classical mechanics. It makes solving physics problems so much easier because we don't always have to track every force, just focus on the energy. So, next time you see something fall or bounce, remember, it's all about energy transforming in perfect balance. Energy is conserved and it's constantly shifting forms to keep the total energy the same. I hope this session has helped you understand how energy and forces work together in the physical world. See you next time with another fascinating physics concept.